Hello, I welcome you all in this presentation related with the subject materials processing fundamentals and practical, and we are talking about the welding of the metals. In this particular presentation I will be talking about the solid state joining processes or solid state welding processes. Okay. We know that so far we have talked about the fusion welding processes where the fin surface is to be melted using suitable source of the heat, followed by solidification of the molten metal to produce the metallic continuity and a weld joint. In fusion welding process, we need to supply lot of heat to ensure the melting of fin surfaces. But in solid state joining processes, basically the joint is developed through the controlled plastic deformation coupled with the diffusion and metallurgical transformation in form of the recrystallization and other phase transformations. So, it does not involve melting intentionally, it does not involve melting intentionally, but uh, if at all any kind of melting is taking place, then that will be due to the unfavorable the welding conditions. So, as far as this presentation is concerned, we will be talking about the various aspects like the need of solid state joining processes, then what are the approaches of development of the joints by solid state joining processes, and then what are the prerequisites or requirement for developing the joints using the solid state joining process or SSJ. Then what are the main mechanisms that contribute towards the development of the joint like diffusion, recrystallization, mechanical interlocking, and sometimes localized melting is involved, and then melting which is there in the diffusion brazing particularly. Then solid state joining processes, common solid state joining processes are like friction welding or friction stir welding. About these two processes we will be talking in detail. Then the ultrasonic welding, diffusion bonding and the roll bonding. About these processes we will be talking in this presentation and in the next presentation as well. Okay. So, as far as the need is concerned, you see in the solid state joining process, we know that the heat supplied is limited because we do not need any fusion, no fusion intentionally of the fin surfaces. Okay. So, the limited heat without fusion. So, this approach wherein with the very less heat input the joint is developed. So, this kind of the approach of solid state joining or the solid state joining process are found to be more appropriate for the metals which are sensitive to the heat. So, heat sensitive metals sensitive to the heat are preferred to be welded by solid state joining process, so that the related thermal degradation in the heat sensitive metal is reduced. Okay. Another one is when we try to weld the materials, different metals A and B, which are not compatible in terms of the physical properties, chemical properties or metallurgical properties, even mechanical properties also. So, because of the difference in the characteristics of the two different metals when we try to fuse them together. So, mixing of the molten metal due to the metallurgical and chemical incompatibilities, what it causes? It causes the very the weld joint which is very poor in terms of the characteristics like very low strength, very high brittleness and very low toughness like that. So, why it happens? Because the compatibility between the different metals may not be proper, or those may be incompatible. For example, fusion welding of aluminum with the iron will create lot of trouble. Likewise, aluminum with the copper will create direct melting for the welding purpose will create lot of trouble. Similarly, titanium with the iron will create trouble. So, when the different metals are brought together and melted together followed by solidification, then they create lot of issues because of the formation of undesirable the phases and the compounds in the weld zone, and that in turn degrades the joint characteristics significantly. Therefore, the dissimilar metal joining where if we use the solid state joining, then they will not be mixing together significantly in the solid state. So, that will reduce the related adverse effects of the incompatibilities, and that is why the dissimilar metal joining can be somewhat joined relatively easily as compared to the fusion welding. Similarly, the dissimilar material combination, say if you want to weld aluminum with the polymers, then certainly because of the large difference in their the physical properties like melting point, thermal expansion coefficient and chemical properties. So, these cannot be fused together directly for development of the weld joint, and in those conditions it is preferred like the solid state joining process is applied. Okay. When we are handling very thin sheets like 0.5 or 500 micrometer or 200 micrometer. So, thin sheets and films, when thin sheets are welded using the fusion welding process, they make the development of sound joint difficult because of the issues related with the melt through, okay, and control over the weld pool becomes very difficult. Therefore, the joining of the thin sheets using solid state joining process is found to be very feasible and useful. So, how it helps in actually how the solid state joining helps in development of the good joints, since our the heat supply during the solid state joining is less, therefore, related thermal degradation in terms of the damage to the microstructure of the parent metal and the properties like in terms of the hardening or softening of the heat affected zone, properties in the heat affected zone, or the development of the high residual stresses. Say these are mostly tensile residual stresses in the weld zone. So, the greater the heat input, greater will be the thermal damage to the microstructure, mechanical properties and the residual stresses. So, in these forms the damage can occur to the parent metal, and that in turn will be degrading the joint performance in fusion welding. So, if you want to avoid that, then SSJ helps in reducing this thermal degradation in terms of the structure properties and the residual stress development. Mostly these develop like compressive residual stresses, and the HZ width is reduced because of the reduced heat input. Another thing is that like during the fusion welding, when we try to melt the fang surfaces for development of joint followed by the solidification. So, we have the molten metal. This molten metal interacts with the atmospheric gases which are around. So, this interaction can be in form of the like the gas is getting dissolved in the molten metal, resulting in the porosity. If they are not, these gases are not able to escape from the molten metal during the solidification. Another thing, these gases can also interact with the molten metal to produce the oxides and nitrites, and these, if these do not segregate at the surface, then these will be left in the weld metal and will be present as inclusions. So, this is the another problem, like the molten metal interacting with the atmospheric gases leading to the porosity and inclusions. There is another kind of problem that is commonly encountered, like if the metal being welded by fusion welding process is having the higher solidification temperature range, then it tends to promote the solidification cracking. If the solidification temperature range is wide, like say 100 or 150 degrees centigrade, then this will promote the solidification cracking or the cracking of the weld along the weld center line. Okay. So, this kind of the cracking will certainly be leading to the rejection of the weld joint. So, if the joint is developed in the solid state, then the solid state the issues related with the solidification of the weld metal, those will be eliminated, because in solid state joining there is no melting of the parent metals. We may have localized melting of the interlayers, fillers for ensuring the metallurgical continuity in the diffusion bonding only. Okay. Then the sustainable fabrication with the eco-friendly process. When the solid state joining process are carried out, since there is no melting. Okay. So, the no vapors or the fumes, metallic fumes which are generated, and there is no harmful gaseous emissions, okay, like in arc welding or the fusion welding. Okay. So, the absence of the metallic vapors and the elimination of the possibility of the harmful gaseous emissions during the arc welding, fusion welding. So, that in turn reduces the possibility of the environmental damage due to the emission of these the metallic vapors or the the gases generated during the fusion welding process by the arc, gas, laser, etc. And since the processes are basically rely heavily on the plastic deformation, which can be of micro or macro level, coupled with the metallurgical transformation in form of recrystallization in terms of the diffusion for development of the new phases at the interface. So, since here we have the absence of the harmful gaseous emissions and the absence of the metallic vapors, that will make the process more sustainable, which will make the solid state joining processes more sustainable and eco friendly. Okay, so this is about the comparison of fusion versus solid state joining. So, as I have said, the heat input, if we talk of the fusion and the solid state joining process. So, for the fusion, heat input is very high and here heat input is low, because whatever heat is generated, that is generated usually under the in situ conditions, except in the diffusion bonding, where the component to be joined component to be joined are kept at a high temperature in the controlled vacuum furnace. Then as far as the melting and solidification is concerned, the fusion involves the melting followed by solidification, and there is no melting and solidification in case of the solid state joining. Then the heat affected zone in the fusion welding, heat affected zone is very wide due to the higher heat input, and here in solid state joining it offers the advantage of having the narrow heat affected zone. And the gas metal reactions like the molten metal reacting with the gases like oxygen, nitrogen and hydrogen, and these will be producing either porosity or their oxides and nitrates in form of inclusions, and that will be degrading the joint performance, promoting the defects in the weld joint, okay, in the weld metal. But here, since the things happen in solid state, so there is no interaction of the atmospheric gases with the molten metal, but certainly due to the higher temperature generated of the metal in the solid state, so there can be some kind of the interaction can take place between the gases. So, that can lead to the decolorization in form of oxide formation and the nitride oxide and nitride formation at the surface. Okay. Then the severity of the metallurgical transformation due to the higher heat during the fusion welding, the severity of the metallurgical transformation and the damage to the microstructure of the parent metal, that is very high, and here it is low or very limited. The residual stresses are also very high, and rather they are unfavorable in form of the tensile residual stresses, and here these are low or these are also sometimes the compressive residual stresses develop. Now, as far as the process capability is concerned, the similar and dissimilar material joining. So, as far as the different metals are to be joined, like metal A is to be joined with the metal B, then using the suitable kind of the fillers or using trimetallic welds, we can develop the joint using the fusion welding, but we need to see like our filler choice is very appropriate, because a direct dissimilar metal joining by the fusion welding usually produces the joints which are not really very good in terms of the joint characteristics. Okay. But in terms of the process capabilities, both similar and dissimilar metals and materials can be joined relatively easily as compared to that of the fusion welding. So, the solid state joining allows the joining of both similar and dissimilar metals as well as the materials with relatively greater ease as compared to the fusion welding. So, as far as the gas emission is concerned, as I have said, a lot of gases are emitted during the fusion welding. So, more gas emission during the fusion welding as compared to the in solid state. So, usually there is no gaseous emission during the solid state welding. Okay. So, this is how we can compare in some of the technological aspects, both solid state and the fusion welding processes. So, because of this only what we find that solid state joining process is preferred for the welding of the dissimilar materials as well as the heat sensitive materials. Okay. Then the common phenomenon that happens during the solid state joining, like the metal A is to be joined with the metal B. So, depending upon the kind of process, it can involve a significant plastic deformation at large scale using the processes like friction welding or friction stir welding. They involve significant plastic deformation. Likewise, the forge welding also involves a significant plastic deformation. So, in that case, so this is one of the aspect where macro scale plastic deformation is involved. There is another category of the processes where at the interface micro level plastic deformation is involved in welding processes like explosive welding, ultrasonic welding, and the magnetic pulse welding. Okay. These processes involve micro scale plastic deformation at the surface. So, this kind of plastic deformation is important for the two purposes. This deformation serves, whether it is macro or micro plastic deformation, it serves the two purposes. One, it brings the metal to it brings the two different metals being joined in perfect contact with each other. So, metal to metal contact is enhanced. This is one, and the second, it also allows the mechanical interlocking. Okay. And when the deformation happens, so the deformation happens, it facilitates the recrystallization of both the materials at the interface, and sometimes the deformation assisted phase transformation also takes place at the interface for development of the new microstructure at the joint interface. So, usually the deformation is always there, whether it is micro or macro scale. Okay. In case of the macro scale plastic deformation, what we will see, what we will be seeing, that the kind of the heat generation due to the deformation and the conditions during the micro scale plastic deformation, they will be little lighter as compared to that in case of the macro scale plastic deformation. So, it will be involving more heat and the more deformation. So, there will be more material of the more parent material will be affected by the heat and deformation, and that will be leading to the wider heat affected zone. Okay. So, some of the processes, as I have said, the friction welding, friction stir welding, ultrasonic welding, magnetic pulse welding, explosive welding, and the roll bonding or accumulative roll bonding. All these basically these involve a combination of the macro and the micro scale plastic deformation. Okay. So, like say these two involve the macro scale plastic deformation and others involve the micro scale plastic deformation at the interface for ensuring the metallic intimacy, bringing the different materials in perfect contact with each other, so that the diffusion across the interface can take place and the metallurgical bond between them can be developed. So, this is one aspect. The second is the mechanical interlocking in forge welding. Like the initially the rods may be like this, but when they are heated to the high temperature, and then what happens, we try to hold them together like this, and when they are perfect in metal to metal contact, a good metallurgical bond between the two is developed. So, since this happens at the deformation happens at a high temperature, so this facilitates at the interface, this facilitates the recrystallization, but this will be possible only if the two components are in perfect metal to metal contact with each other, and to ensure that during the forge welding especially we use flux, so that the impurities present at the surface can be removed in order to bring the perfect metallic intimacy and reduce the defects at the joint interface. Okay. So, this is the another one where significant plastic deformation is involved, and the mechanical interlocking strengthens the kind of the joint which is being developed. Okay. But whenever, like say, whether it is the macro or micro scale plastic deformation, so in all the cases, not just the plastic deformation will be happening, but some heat will also be generated. This heat can be generated by the interfacial friction across the interface during the welding, like say friction welding, okay, and then friction ester welding, ultrasonic welding, okay, ultrasonic welding, all these involve the friction frictional heat generation at the interface. Magnetic pulse welding, like explosive welding, and yeah, so these two welding process involve severe impact. So by the impact, like the kinetic energy is converted into the heat. So but the heat generated is less, but still micro scale plastic deformation coupled with the minor heat generation. Okay. So whenever the friction is involved, heat generation is much more as compared to the case when there is just impact, like in electromagnetic pulse welding and explosive welding. So you see, whenever there is, you see, plastic deformation has facilitated the perfect metal to metal contact, coupled with the deformations. Once the plastic deformation has happened, enough heat is there. So what will happen? Deformation of the material at a high temperature facilitates the recrystallization. So formation of the new grains at the interface. Okay. So interface will not be left, but across the interface will you find that there are new grains. Okay. That is one. Since the heat is generated, so that also facilitates the diffusion across the interface. So the diffusion, when the diffusion takes place, there will be formation of the new grains. Okay. Sometimes the new phases are also formed. Okay. And this can also change the grain morphology. Okay. So the metallurgical bonding, like say, that will be developed, metallurgical bond will be developed through the diffusion, recrystallization and the phase transformations at the interface. So when the solid state joint is developed, you see, it will be involving plastic deformation coupled with the heat, either it is heat generated under the in situ conditions, or the components to be joined are kept on in the at the high temperature, in the high temperature vacuum chamber to facilitate the diffusion across the interface. So let me talk about that, the one process where the diffusion plays much bigger role as compared to the deformation. So that process is called the diffusion bonding. So what happens in that? Say there is a vacuum chamber. Okay. This vacuum chamber, like say, maintain 10 to the minus 3 to 10 to the minus 7 torr depending upon the kind of material. Now accordingly, we select the suitable temperature, say 500, depending on the metal combination, say 1000 degrees centigrade. Okay. At high temperature, when the two components are kept under pressure, so having the perfect finish and good metallic continuity is established under the pressure. So the diffusion of atoms across the interface. So because of this pressure at high temperature, micro level plastic deformation facilitates the metal to metal contact. So in diffusion bonding also, we will see that the micro scale plastic deformation at the interface is facilitating the metallic intimacy, and once that is developed through the collapse of the peaks and valleys which are present, once this is done, then based on the concentration gradient of the alloying elements, the atomic movement from one side to another will be taking place across the interface, and that in turn will be helping to develop the metallurgical bond at the interface through the diffusion. Okay. So even here in diffusion bonding process, where the diffusion plays a bigger role, the micro scale plastic deformation is involved. Okay. So as we have seen that since the joint is developed in the solid state itself, okay, and so what is important for development of the joint? One, like if at the all, all the surfaces, all the components at the surface have lot of impurities. These may be in form of the adsorbed gases, or their compounds in form of the oxides and nitrites. Additionally, there will be lot of ups and downs, peaks and valleys present at the surface. Okay. So if we want to see that the joint is developed and metallurgical joint is developed across the interface, it is very important. And to develop the metallurgical bond across the interface, it is very important that these impurities are taken care of. Otherwise, these will be left as inclusions, or they will not allow the diffusion to happen across the interface. Okay. So the cleaning of the surface is one of the most crucial thing in solid state joining, and therefore according to the metal, we can use a mechanical cleaning like use of the emery paper or the wire brushes. Then we can use the chemical cleaning using suitable alkaline or acidic solutions. Then we can use the ultrasonic cleaning also, where in the suitable environment or liquid the sample is placed and the ultrasonic treatment is done, so that the surface impurities present or at the surface are removed. So, idea here is to just take care of impurities which are present at the surface, so that surface can be made free from all these kind of the impurities which are present, and then when the two components are brought in close contact with each other, subjected to the plastic deformation, whether it is macro scale or macro scale or micro scale, then it will be facilitating the good development of the good metallurgical bond. So, for certain processes like the diffusion bonding, okay, it is very important that surface roughness is maintained to very low level, say for example 0.1 micrometer. But if it is processes like friction welding, friction ester welding, or the roll bonding. So, in those cases the roughness may not play a very big role. Okay. The role can be played is like in roll bonding, if the roughness is great, then there will be mechanical interlocking across the interface due to the greater roughness. Okay. So, the roughness is very important, but that has to be seen considering that has to be, so desired roughness is to be maintained as per the kind of process to be used for development of the solid state joints. Okay. The straightness and flatness, this is also crucial, especially for the diffusion bonding process. Surfaces must be straight and flat, otherwise what will happen, the contact will be there selectively in half portion, and then in the remaining portion may not be in contact at all. Okay. So, this portion is in contact, but remaining portion may not be in contact if the flatness and straightness is missing. Okay. So, that is the another aspect. Surfaces must be cleaned to remove all kind of the impurities from the surface. Surface finish must be, desired surface finish must be attained, especially in case of the diffusion bonding, and the then straightness and flatness also is to be realized through the controlled the surface preparation using machining or whatever the process is being used, like the shaping or grinding. Then another aspect is, so once the surfaces have been prepared, okay, then a good solid state, the good joint using the solid state joining process can be realized only if the surfaces can be deformed at large scale or at micro scale. So, depending upon the process, that requirement will change. So, micro scale plastic deformation or the micro scale, for macro or micro scale plastic deformation, it is necessary that the material is having some good ductility, say in terms of the percentage elongation or low yield strength. So, if the material is having higher percentage elongation and the lower yield strength, then the plastic deformation will become easier. Okay. So, out of the two metal systems which are being joined, out of the two components, say at least one metal should have reasonably good ductility, okay, in order to ensure that it fills the gaps which are present at the interface when the solid state joining is performed. So, it is preferred that the material is having low yield strength and higher percentage elongation. If not both, then at least one metal should have, and this is especially important if we are using the macro scale plastic deformation like friction welding and the friction stir welding. Okay. In these processes it is necessary. Likewise, in ultrasonic welding, at least one component should have the reasonably good percentage elongation, so that it can develop the good metallurgical bond and ensure the good metallic intimacy at the interface for developing the joint. Okay. Then other two characteristics are that which will be affecting the plastic deformation. Since the plastic deformation is key in solid state joining, so if the material is showing the higher work hardening characteristics, then it will resist the deformation of the material during the solid state joining process. So, it is better, or it will be easier if the material is having low work hardening capability as compared to that of the material having the higher work hardening tendency. So, that is about the work hardening. And thermal softening, like say either heat is generated under the in situ conditions or it is externally applied, external heat is applied. In both the cases, You know, we know that when the metal is heated, it loses its yield strength and helps in increasing the percentage elongation. So, but the different materials show the different trend with regard to the thermal softening. The materials with metals which show the greater thermal softening, they will be easier to weld using the solid state joining processes. The joint development of joint for the metals showing the high thermal softening tendency, those can be welded relatively easily as compared to the metals which do not show. Okay. Why? Because the metal will be with the heat generated either under in situ conditions or externally apply heat. In both the cases, it will lose the strength, its yield strength will be reduced and the ductility will be enhanced, and that in turn will facilitate the development of the joint by solid state joining processes. So, now here I will conclude this presentation. In this presentation, basically I have talked about the need of the solid state joining process, comparison of the solid state joining processes with the fusion welding, and then what are the characteristics material should have for development of the solid state joint effectively and easily. Thank you for your attention.